Hello, we are Team Dinonaut 2005-02 from Thailand, and so for this season, we participate in first uh, Thailand Championship, and we are part of FTC team for 2 years. For this season, we got Inspire Award and winning Alliance Captain, and we got advancements to World Championship.
During the qualification season, we saw like gameplay become much faster, and early on, many teams focus on basic scoring and consistency. But as the season progressed, cycle time become like shooter and autonomous routine became like more advanced. So like and also like defense also
Yeah.
become more strategies, especially like against like like the team that can shoot many ball. So we have to like defend more.
This is our robot for this season. It is a robot that we use on our Thailand Championship. For our robot, we separate to the modular development, so we can develop each modular at the same time. So for the intake part, at the Thailand Championship, we use the rubber band, but right now we just change it to the gecko wheels on the front, and when the ball comes, we'll go to the next part will be the middle take right here. For the middle take will be the smaller gecko wheels, and it will go through into the middle of our robot. When we're going to shoot, this will be the flap right here. So for this one,
Like
this will push it will push inside when we shooting. And for our shooting part for this turret, so this one we use just one Exxon servo for powering the turret. In the front of our shooter, we have the lamplight camera, so we can detect the goals and like shoot while moving. For the flywheel, we use the Rhino wheels, with adding the weight on it, so we will be more momentum while we shooting.
yeah,
And so for our robot, this will be like fully 3D print. More than 70% part of our robot will be 3D print. For the hood of our shooters, right here, the combination will be only at the top of the hood. So when it shoot, it will be less friction while we shooting, and we use the nylon PA filament, so it will be slippier than like other filament. For our drive 10 in this season, we use the parallel pit drive 10, this one, and for localization in the field, we use the OTOS sensor, the optical odometry from SparkFun. For last season, we use pinpoint, but for this season, we see, oh, this one maybe like
easy to mouse.
it will be easier to mount, and like it will use less space than the pinpoint. So we're trying it and it's worked. So we like right now we're using it. We bought it like two or three of them for the like spare part. But we found like a problem with like when the field have like the dust, maybe like some dust. So yeah, but we have to clean it a lot.
Yeah.
In Thailand Championship, for in game we use this part for in game is will be the zip chain actuator part.
Yeah.
So it's really the chain that come together to be like one stick. So it's really like very strong for that. And but we found like many robots in Thailand is really big. So in our Thailand championship we change it to the half lift mechanism. So this one can lift our robot in half. We can move while we parking. So we will have space for other robot to park. Right now we are working on our new prototype of our robots because our so this one is the drive train is really big, so we don't have like enough space for the intaking part, so we're going to make it have it will be like the drive train will be shorter, and we will have like the front space for the intake, and we can uh use the so right now we are we are separate the mortars, so the intake will be one mortars, middle take will be one mortars, so we're going to use it all just only one mortars.
So I guess we were starting out with like how stuff has changed over the season in our region. Um, and I mean, I think personally from what I've seen, there's been a lot um, in the area of intaking like straight from the gate zone. Like a lot of the higher end teams in our region have started doing that for their autonomous. Recently, we've been working on ways to develop our robot to be able to do that as well, to compete with those teams. Um, so right now, Josh, if you want to talk about some of the things we did to try and get ourselves there.
So before on our robot, we had an intake in the front, which was way smaller than this, but
About this size.
it was about half the size really, and it didn't allow us to grab from the gate fast enough. So we made our intake as wide as the whole front of our robot, basically, so we can grab balls from anywhere, basically in the front of our robot, not just the center. That definitely improves the speed for how fast we're able to grab in teleop.
We were testing it, and like this is like very loose testing, but in 10 minutes we about doubled the amount of artifacts that we were getting in the goal. So we went from like getting around like averaging like 18 on our own to we're going to be averaging around 40, which is pretty good. The major reason for this was to fix up our autonomous, so we haven't gotten around to actually editing it yet, but for the previous competitions, we had a 9-ball auto, so we were going at just getting the preloads and the first two lines. But we cut down on some of that time there. We changed our shooter compression, so it's a little less compressed. So it's like quicker to get the balls out of the shooter. So the ball really just like it slides in there really nice. And so that allows us to get an extra 10 seconds in auto for us to get more artifacts in. So that's we're going to be able to get a lot more in. And especially with the recycling from the gate, like we plan on doing, we should just be able to keep it going the whole time really easy. Most teams are still just shooting from like their one good point on the triangle. So there's been a bit of like defense on those teams that are only able to shoot from one position, like taking that position from the other team. Our robot is able to shoot from anywhere on the field, so like being able to shoot from the back triangle is an advantage this season because not many teams have went for that route. What we're doing for our shooting mechanism is we're doing the larger blue wheel there that's got about, I think, 2 flywheels on it. And that's being powered by a Gorilla Bear 6000 RPM motor. And then we've got up on the top another smaller wheel that's also powered by one of those motors, but it doesn't have the flywheels. And basically what we're doing is we're keeping the bottom one at a consistent RPM, and then we're changing the RPM of the top wheel to adjust for distance from the goal. So we're getting a linear regression for how fast we have to be shooting to be able to score on the goal from anywhere. So it's like automatically adjusting to be wherever it needs to be. At competition, we had found that there were a lot of teams either just weren't using a camera at all, or there was a lot of teams that you could easily block by just being in front of them. Because the camera would no longer be getting data. And so all of our calculations for like the turret and the shooter are all done based off of the pinpoint. We've got the limelight on here so we can get working on able tag localization and like filtering between that. We'll probably still continue using the pinpoint for like turret math and shooter math. But just like having this double check on where you are is nice. We used to be doing a hood, like everybody, a lot of other teams are doing like the adjustable hood here to redirect the angle of the ball. But we ended up not going with that. We changed it to this powered top wheel, and that's been working really well and consistently for us. And I mean, like, it's just a little more robust than dealing with the servos that we had to deal with when we just had the hood on there. I think we changed that after like our first competition. That was like one of the first things we went for was changing that.
Originally for our shooter, we had the motor in the back and we had a belt going to the front. But the issue of that, there was so much friction from the belt, and it actually made it impossible for the motor to recover quickly after we shot a ball and maintain speed when we were giving it power.
Even with the 3 flywheels.
Yeah.
We've got obviously a turret going on over here. It's just a turret. It's powered by currently 1 servo, but there are 2 servos mounted on it. And then we've got our intakes got 2 motors, and it's basically a streamline of we've got this rubber band roller, and it goes into 2 sets of smaller wheels, and then another smaller wheel, and then an even smaller wheel in here to get it into the kicker, and then we've got 2. I don't know if you can really see it at this point, but there's 2 GoBuildo boot wheel things going on back here. You really can't see it. But essentially what those are doing is they're bridging the gap from the shooter, like the top of the shooter here above the bearing to below the bearing. We've got a similar thing going on to our predecessors at Dinonauts. So this is, we did the Robot in 30 Hours challenge, and this is one of our first ideas was these egg-shaped cams here. And so they elevate the robot. They're not powered, right? So Josh is holding it up manually. But so these guys are pushing the robot up onto this back wheel so that we're only taking up half the space and aren't lifting the whole robot. And those are just powered by servos. The last aspect of this robot is we've got a bunch of little bit of driver feedback going on back here. So these are 3 GoBuildo LEDs that are inside the intake. There's a couple color sensors. There's 3 color sensors. And what we're planning on doing is having each of these like go green, purple, purple for like which balls that we have in the intake, because we don't have like a spindexer or anything that's indexing these colors. And then these strips here are showing like the rev of the shooter wheel. So like when we're revving up the shooter, it like they'll go red to orange and yellow, green. We can also go over there's on the bottom of this robot, these are 2 of the color sensors that I was talking about. But on this robot, we are using the GoBuildo pinpoint odometry that we were talking about before. And we've seen a lot of teams using this year, and it is really accurate. We ran it and it worked within millimeters as soon as we put the offsets in. Like it was working beautifully right off the bat. And so we've had a lot of success with that. Last year we were using the Spark Fun OTOS, and it was kind of like it was on and off. Like it worked really well when it worked, but it just got like dusty so quickly, and there was so much upkeep. And especially last year when it was possible for your robot to fall from like the ascent onto the Spark Fun, like straight onto it, it was like a little dangerous for it. And so we went through a lot of them last year. And so this like nice robust solution is really nice.
So what we've noticed throughout the whole season in New York City, we found out that in the beginning of the season, we saw, because we participated in Robot in 30 Hours, we saw everybody focusing on a human player intake. And then later on, towards the first qualifier in New York City, which we attended to, we saw all the teams shift to like a ground intake after that point on. And then from there on, we started seeing auto start going from three artifact auto to going up to 9, going up to 12, and then we started seeing teams start implementing 15 artifact auto by opening the gate and intaking it until the new rule came out where the ball has to pass through the gate first. So teams started shifting by opening the gate and then moving to the side for intaking those 3 balls, or intaking the 3 artifacts all the way at the end. Then we saw teams start prioritizing close range shooting rather than far range shooting because they found out it improved their cycle times during auto, during teleop, towards all that time.
Some other changes I saw like during the visually on the robot was the intake. Like before, I saw teams use like a small intake, not very wide, nothing like that. But I saw later on teams started using vector wheels on the sides of their intake and like rollers and their intake to make it easier to grab from the corner of the field, to make it more compatible with the other teams also.
We did a lot of iterating with our robot. In the beginning, during robot in 30, we started with the rubber band intake, but we realized it wasn't the best. And a lot of teams started using sushi wheels, vector wheels, medical tubing, which we currently have all 3 on our robot. We started from the rubber band and then we iterated to doing a dual intake, but we realized with space it didn't work out. And then we integrated to doing sushi wheels and medical tubing. And then we discovered vector wheels, which a lot of teams are starting to use vector wheels. A lot of communication, we ended up designing our own. And now we include all 3 on our robot.
Our first design of the shooter was very like bulky and very wide. We had a lot of it was very simple and wasn't that complex to design. But then we realized going through the season that teams started making the shooter very thin, adding the motors, the flywheel motors to the front instead of the back to make it more smaller and make it really small to fit the robot and make it high up on the robot. So here we changed to this design. You saw many teams use it. It's a very thin hood, nothing too complex, and a very big very basic flywheel with belted. That we switched to that. Before we had all motors in the back and we had a chain to the forward. And this design is very good. It's very quiet. It's nothing too complex on the field.
As also to add on to the shooter, to go along with what we were saying, also you did the hood. So at first we started with a very wide, bulky, very large hood that we didn't end up utilizing during the season because we were more focused on power rather than using the hood. And now we ended up changing, which we switched. We use more hood rather than power. So the other day when we were testing, the hood, when the hood goes up, it makes an arc. So when the artifacts go into the scoring zone. So the higher the arc, the better you have, so you utilize less power. So we switched from a very wide hood to a very small and narrow that works even better because we can easily maneuver with 2 servos, the hood, to create an arc so the artifacts go into the goal. Also, to add on to iterating, for our drivetrain, this year's robots are either very small and narrow or they're more boxy and larger. Our first robot was a very heavyweight robot and it was very large. One thing to add on to that is we had control expansion and all of our hubs located in the back. But at the moment, we switched to our V2 Phantom, which we have everything on the sides, control expansion, odometry. For the servos, everything's on the side. So this robot's a lot more lightweight. So when it comes with lightweight, it can move faster on the field. Those are major iterations we made.
I think I can start out with just kind of the general strategy we've noticed in our season. So Washington is known for putting up really high scores, but what we actually realized going into our KPIC semifinals or super qualifiers was that defense and actually playing for penalties would be a key component of how games are played. So rather than just going for the maximum amount of cycles and most amount of points, we had to actually then basically account for other robots that are trying to protect their own gate zones or secret tunnel zones. And that's something that's had to change how we drive, especially, and how much what our intake path is on the field. Yeah, that's kind of the biggest change that we've seen throughout the season. And we really kind of just focused on rapid fire throughout the entire season, right from the get-go. And then really the only thing that's changed is the intaking from our analysis.
Right.
So,
yeah, we have a lot of iterations that we went through for our robot. One of our key iterations is our intake. We started out with a pivoting intake, However, it had a lot of issues. It was not only very vulnerable to shocks and collisions, but it was also very unreliable. And that was the biggest thing that was impacting our cycle times, and it was ultimately being able to rapid fire during the interlake. So this is one of the things that we changed and iterated to a static one, and we did gecko wheels without any mechanism wheels. You lose some of the touch it, own it power that you get, which is why we opted only for gecko wheels here.
We basically, it's kind of hard to see, but in here we actually have 2 motors powering our intake. So what this allows us to do is have essentially 4 motors directly dedicated. So you can see there's 2 pulleys and belts that connect to the intake. Basically, we have 4 motors just powering the ball through the entire robot and its ball path, which is a lot more efficient than other designs that we've seen where you're using a motor for a spindexer or a turret. So we found that really utilizing all of the maximum just like raw power that you have available with 4 motors makes being able to rapid fire a lot better, which was the key kind of component that we were going for in our game strategy.
So I think we were struggling with having some twitch or some slight oscillations when on earlier versions of it. So one thing we made sure to have was very little backlash, mechanically speaking. So when here I can hold the servo, because I can see there's very little backlash on mechanically, so that helps reduce the twitch. On a software side, we did initially use CR servo mode. However, that did include slightly more oscillations as well. It was technically faster, but ultimately because these servo gears do look very large, but don't be fooled by them. This turret servo is actually on a 1-to-1 gear ratio. So we can actually just use servo mode and get complete control over it at its specific position. And the thing about servo mode, you can just give it a position and the servo will automatically go there, and it'll have very little backlash and very little jitter around.
The last part, like with software, is we actually also, another iteration we had was to add this external encoder. So we have an external encoder gear right over here. So this basically allows us, because it's 3D printed, we can basically just fine tune the 3D printed tolerances on this and basically get it a lot finer tuned. We can get a lot finer tuned. Right now it's slightly big, but this allowed us to basically have very accurate positioning of our turret, and we're able to know exactly where it is throughout the match. So we use both the absolute encoder to first kind of get the relative encoder to know where the turret is, and then after that we can just use the relative encoder for the entire match, and that gives us very precise readings on where our turret is.
One of the things that has changed a lot as the season has progressed is like how optimized some robots are. So like at the beginning of the season, many robots were still struggling with like scoring. Definitely like in North Carolina especially, people were more optimized towards the time that states came around. And so the way we handled that was trying to play a little more defense whenever we could. So like for example, whenever we cycled the far zone, we would every now and then we just like bump into the other alliance just to like stop them from scoring. And so that would sometimes give us the upper hand. Also, I guess teams also use that strategy on us as well. So we added shooting while moving, and this allows us to like shoot under defensive scenarios, which has been pretty good for us. So this year's robot for us is pretty standard compared to like the rest. We have a gecko wheel intake that is compliant, and basically it has like this adjustable angle thing so that it can like adapt to the shape of the ball. And it just basically stores 3 of them in this little like funnel over here. And then when we're ready to shoot, we have a gate powered by the servo on the shooter. And when we're ready, we just open it. And then our turret handles the aiming. And then our flywheel just spins up, and then we take our shots. And that's how the flow of the game works when we're driving around. So we're using odometry primarily. So we have a go build a pinpoint, and we have 2 odometry pods in the back. But as like the season progressed and as time went on, we noticed that like defense and stuff was messing with the accuracy of our odometry, and it was causing a lot of drift. So we added an RGU cam. If you can see it, it's right here. And what we do with this is we scan the AFO tags on the goal, and based on that, we get our position data about like where we are, and we update our position accordingly. So it's like a mix of sensors that we use. So whenever we see an AFO tag, we update the robot's position, and then that way we're always like dead center whenever we need to aim.